Hello everybody, today I'll show you how to do problem 8 from Unit 2. So, this problem states, consider the cubical closed surface having sides of length A as shown at the right. It is placed in a region where there is an E field parallel to the x-axis. Find the total flux of E through the surface and the total charge contained within the cube if A, E is uniform, and B, the magnitude of E varies according to E is equal to B plus Cx. Okay, so to find the total flux of this system, we're going to first take the sum of flux, and we find that by considering which surfaces the E field passes through. In this case, it only passes through two surfaces. The rightmost surface, which I'm going to call A1, and the leftmost surface, which I'm going to call A2. As you can see, it will not pass through any of the other four surfaces since this E field is going directly horizontal. So now to find the sum of the fluxes, we're going to use the formula, which is the integral of E dot dA. And I'm going to say that's E dot dA 1, and then add that to the integral of E dot dA 2. Okay, so since part A says that E is uniform, we know that's just constant, so we can bring it outside the integral. And that leaves us with dA. And as you know, the direction of a surface is perpendicular to the surface. So therefore for A1, the area vector would be pointing right this way. For area 2, the area vector would be pointing in the negative x direction to the left. Therefore, if we would say that this is dA cosine 0, since the E field vector and the A area vector are in the same direction. Now, for this side, we have dA cosine, and this is 180 degrees since they're running in opposite directions. That will get you E. The integral of dA is just A. Cosine 0 is 1 plus E A cosine 180 is negative 1. Therefore, your net flux is 0. To find the charge within the cube, we need to remember that flux is equal to E dot dA, which is equal to Q over epsilon. Therefore, as we've seen above, our net flux is 0. It's Q epsilon, and that means that Q is equal to 0. And that is the charge within the cube. Now, moving on to part B, we are going to do the same thing, except now the E field is not uniform. Starting off the same way, we're going to write the sum of flux is equal to the integral E dot dA 1 plus the integral of E dot dA 2. Okay, there we go. And now we are going to substitute in the equation for E, which is given to us. And they said it was E is equal to B plus Cx. So plugging that in, we get B plus C x times a plus b plus cx times negative a. Okay, this is for area 1 and this is for area 2. So we know at area 1, x is equal to a, since area 1 is at this x coordinate right here. And that's a distance from the origin. So we're going to plug that in for x. So we get b plus c a, where little a is the distance from the origin, plus, and for the surface 2, that x coordinate is at the origin, which is 0. Therefore, we get BA, or AB plus AC times A, plus negative AB plus or minus 0. Now, that will get us, these cancel out, so that gets us A times CA. A is the surface area, or the surface area of one side. And since this is a cube with side length A, or uppercase A, is equal to A squared. So therefore, the answer is C little a cubed. So that is your net flux. Now, if we were to find the charge, we again say that flux is equal to Q over epsilon. We found that flux is equal to CA cubed. Therefore, the charge is equal to epsilon times CA cubed. And that is your final answer for part B.